following podcast is made possible by our great sponsors. Carrier and Carrier.com, makers of all sorts of great equipment, controls, and everything else. You know Carrier. They're who we use for equipment at Kalo Services, my company here in Central Florida. And you can find out more at Carrier.com. Fieldpiece at Fieldpiece.com. Fieldpiece makes a lot of great instruments, but specifically, I've been talking a lot about the MR45 recovery machine and the VP85 vacuum pump. If you haven't taken a look at these two products, ask for them at your local supply house or take a look at TruTechTools.com. You're going to like the features and benefits of this vacuum pump and recovery machine. They're very quick, they're very quiet, they use DC motors, they work better even at lower temperatures and with voltage drop. There's a lot to like about the Fieldpiece MR45 and VP85. Also want to thank our sponsor, Refrigeration Technologies. They make a lot of great products, and one of them that you're going to want to take a look at is the EVAP Plus cleaner that can be used on evaporator coils. It is a non-rinse cleaner. You don't need to rinse it. It uses enzymes in order to break down the nasty stuff without using harsh chemicals. Our customers like it, our technicians like it, and we use it on every maintenance. That's EVAP Plus from Refrigeration Technologies. Find out more by going to refrigetech.com, or you can also find many of their products at TruTech Tools. Also, Navac at navacglobal.com. If you haven't taken a look at their hydraulic expanding swedge tool, it works all the way from 3/8 to 1.125, which is exactly what we need out there in the field. The model is the NTE11H. That's the NTE11H. Really nice tool, very compact. I saw it demonstrated at AHR, and it does the job from 3/8 to 1.125. Find out more by going to navacglobal.com. And finally, Speed Clean. Speed Clean creates a lot of great cleaning solutions for the HVAC industry, specifically for residential like commercial. They make a lot of different products, and the one I'm going to talk a little bit more in the middle here, but the bucket descaler is a product you're going to want to take a look at. It's a very interesting application for descaling water heaters, for descaling water source heat pumps, anything with a water heat exchanger in it. You can find out more by going to speedclean.com.
And now the man who knows the secret formula that caused old capacitors to last forever and the new ones to fail every 10 minutes. Brian Orr.
Hey, so you've made it to the HVAC School podcast. We're down here in the middle of HVAC School Town in the district of HVAC School, and here I am in your ear holes. So thanks for inviting me there. This is the podcast that helps you remember some things that you might have forgotten along the way, as well as remind you of some things that you forgot to know in the first place. And today we're talking about VRF and VRV, more on the design side, design and selection side, with my good buddy Jordan Cummings. Jordan was a VRV, VRF technician until he moved over to the dark side and started doing more on the rep side of the business, but he's still true blue as far as I'm concerned. And those of you who are interested in VRF, VRV, or work in that industry, you're going to enjoy this conversation. So here we go. Jordan Cummings talking about VRF and VRV. Thanks for coming on HVAC School, Jordan.
Absolutely. Excited to be here.
So Jordan has been in the group. When I say the group, it sort of sounds like a very specialty or exclusive. What am I looking for here?
We're a pretty tight posse, all of us.
A posse. That's what I was looking for. Yeah.
Yeah. We're a tight posse.
Yeah. And Jordan, you were there pretty early on. I mean, I remember seeing you.
I'm hard to miss.
Yeah, that's true. And maybe I remember you more than anyone else because you wore a beer can cold t-shirt while at the gym and kind of flexing it a little bit.
I do what I can. I was just supporting you, Brian, really. I was trying to bring that HVAC school to the Midwest.
Okay. I appreciate that. So yeah, Jordan's been around for a while, contributed to the group, and we appreciate it. And now Jordan has moved in out of the field and into a position where he's doing more training on a very popular topic, which is VRF/VRV, depending on your flavor. So go ahead and real quick and just tell us how you got into this segment of the industry and why you like it and why you're doing what you're doing now.
Like you mentioned, I've been a service tech since I was 18 when I got out of school. Went to a trade school to get my foot in the door. Got into the service industry pretty quick. Got in a truck, and probably 6 years ago was when I got my first taste on a VRV system. It was a Daikin, ironically, but it was a pretty large system. I mean, I think we have a little over 300 indoor units there. So I went from not a lot of experience to I got thrust into it pretty fast. Since then, I've been involved in LG installations and service, Mitsubishi installation and service. Those three are about my extent of experience in the field. So as I was looking to move to a different area, I reached out to my local manufacturer's rep, mechanical sales. They were kind of my go-to support for VRV and VRF stuff. I reached out to him and I said, hey, which contractor is doing a lot with this? At this point, I'm almost borderline obsessive with VRF. My home life, I'm researching different things, comparing engineering manuals and comparing the data between the different manufacturers. So I reached out to him. I said, I want to come work for a contractor that's doing a lot with VRF, right? After talking to them a little more, they decided to create a position for me. And I've come on board with mechanical sales, which is a Daikin rep among other manufacturers. And my role here is just kind of be their VRV specialist. So I help in the layout and design when we're working with engineers. I do a lot of presentation for engineers, consulting engineers, do a lot of presentations for like design build contractors. And then even end users get involved. We'll have school districts come into our office, and we got a training lab, which is a full classroom with whiteboards. And then we got a actual lab with full working heat recovery and heat pump systems that I can kick the tires on and show people.
Yeah, pretty groovy. I think a lot of guys are jealous right now, but yeah, good on you for reaching out and making that happen. So let's start with the basics here. We're going to hop right in, as they say, like every podcaster does. It's like, hey, let's jump right into the nitty-gritty content here.
I dig.
Okay. We talked quite a bit already about VRF, VRV with John Oakes, but let's just step back real quick because you have a nice way of describing it. What is VRF, VRV for somebody who's like, why would I do anything other than what I'm used to?
Sure. Like John mentioned earlier, VRV and VRF are exactly the same thing. Daikin just trademarked the VRV thing. So sometimes I call it VRF, sometimes I call it VRV. Throughout this podcast, I might change it up, but they're both the same thing. To answer your question, though, I've always told people, think of a VRV system or the VRV heat pump system as a hydronic system. It's no different than we got a central plant, which is our outdoor units, and we're providing hot or cold water to all of our indoor terminal units. You could have a heat pump, which is going to be much like a 2-pipe hydronic system. So everything needs to be all in heating. And then in summer mode, you would switch over to be in cooling. The difference is with a heat pump, you could switch back and forth as quickly as 15 minutes. Compared to water or ductwork, I can move a lot more heat in a smaller piping. I don't have to worry about freeze conditions. Probably not a big deal for you guys down in Florida, but up here in the Midwest, cold climate. We're designing around cold climate conditions all the time. So that's a big deal. And then it's typically a lot lower equipment cost, right? Instead of putting in a central plant with all that hydronic piping, custom controls, a lot of duct work, there's going to be a lot of balancing involved with a hydronic system. A lot of that stuff kind of goes away, and that's kind of all built into that VRV package. So it becomes pretty attractive when you start looking at the numbers, especially when you start looking at the efficiencies of some of these systems.
Quick devil's advocate, though, because I'm sure there has to be some things that, so say you're making the decision to go, you're choosing between hydronic and VRF, VRV. What are some of the things that you really have to take care of in order to make sure you don't have issues with VRF, VRV?
Just like anything, I think a really good install and having good installation practices is key. And it gets really highlighted and magnified when it comes to a VRV system. I mean, we talk about using nitrogen when we purge. That becomes a very, very big deal when we have a large network of piping. We talk about evacuating our systems properly to below 500 microns and doing that static vacuum test to make sure that we've dehydrated our system. Most VRF system manufacturers, as far as I know, are switched or are using a PVE oil. Actually, me and Ryan Finley have had some really good conversations lately about this and the characteristics of PVE oil. But we're talking about where if you don't get that evacuated and dehydrated correctly, you can run into issues with sludging up and changing the viscosity of your oil, actually. I would absolutely say your nitrogen purging, your evacuation, and being really thorough with your control wiring are the three big things when it comes to VRV installations and the longevity of it and the reliability.
Yeah, I got a little ahead of myself there, but I just wanted to put that out there because I think another thing that comes up a lot, and John and I talked about this, is that whenever you're dealing with that much refrigerant, because you have a lot of different indoor units, you're not just moving water through, you're moving refrigerant through the entire building.
Sure.
Proper leak detection, proper practices in making flares, or if you are doing braze connections, making sure that all of that is done completely leak-free, and your pressure test and all those things become maybe a little more mission critical than in a lot of other applications.
Yeah, no, absolutely. I guess it doesn't take a specialized person to maybe run some water lines when you're dealing with hydronic. You run those water lines. If it leaks, you tighten it up a little more, right? So you don't have to be let me say, perfect the first time when you're dealing with hydronic systems, installing all that piping. And there's some balance issues that come into that. And that kind of comes into the design part of it. I'm pretty hands-on with all our projects. I follow up, do a lot of job walks, make sure that we're actually measuring our pipe. And if there are any changes to the original drawing, that we're following up with that. So there's things like that where if you purchase or go down the path of a VRV system, if you don't have that kind of support and, you're not building your as-builds as you go and making sure you're following all those rules, you can make a VRV system turn into a real nightmare. But if you're diligent about it and you have some experience, then you can stay out of trouble and it becomes a really efficient, reliable system.
All right, so this podcast is about sort of the design and layout of a system, and we're kind of going to start off with this, a little bit of what we've already talked about, which is how do you choose what system you're going to install? And you alluded to this, but let's get a little more nitty gritty. If you're choosing between a heat pump and heat recovery type system, how do you decide? I mean, what are the factors that would make you choose one over another?
The biggest thing is going to be your occupant type. If it's going to be a bunch of hotel rooms, you're absolutely going to do heat recovery, right? That person that wanted to stay in that hotel for the evening, if they want heating, they're going to want heating right now. They're not going to want to wait 15 minutes for that unit to switch over into the adjacent mode. Heat pump, I use that a lot for like when they're doing church remodels, a lot of open spaces. Maybe if it's all interior space and we really don't have a lot of heating that we're going to see on the system, I'll go with the heat pump. So a little bit of it's a climate, but a lot of it's that end occupant and the expectations, right? Like heat pump is always going to be a more budget friendly system. We try to have that conversation up front with the contractor, engineer, and then most importantly, the end user. What's your expectations? Some of these courthouses or things like that used to only run on steam heat, they're just thrilled to have air conditioning in the summer. They can accept the fact that during those shoulder seasons where I might need a little bit of heat in some space and a little bit of cooling in some space, they're more than happy with the fact that it can switch back and forth as quickly as every 15 minutes. Does that make sense?
Yeah, for sure. And so it's the expectations of the customer, budgetary concerns, and how the space is being utilized. Is the budgetary difference significant in your experience from recovery to heat pump?
I wouldn't say it's significant. Off the top of my head, I mean, there's so many variables that can be played into that. A heat pump, potentially, you could be looking at maybe 2/3 of the equipment cost because we eliminate all those branch selector boxes. And then the outdoor equipment themselves are a little bit more simplified because of some of the reversing valves and things like that you don't need in a heat pump. So as a general rule, I would say maybe 2/3 to 3/4 of the equipment cost if you could go to heat pump.
Another way that I would sort of maybe say this for people who aren't used to hydronics, so you give a good hydronic example there, but we're used to going from straight cool in, say, the residential and light commercial areas. We're used to going from straight cool to heat pump. And so we have an upgrade there as far as the capabilities of the equipment. And so heat recovery is almost like a heat pump on steroids. So it's like making another leap upwards from what you would do from straight cool to heat pump. Now you're going from heat pump to like mega heat pump, where you're basically reusing some of that diversity, I think is the term that's often used within a space in order to move that heat around within the space versus always removing it to the outside of the building.
Yeah. And I like to always say it's like a 2-pipe and a 4-pipe system, hydronics. 2-pipe, you only have 2 pipes going to your air handler. And whether our centralized equipment is in heating or cooling, that whole 2-pipe network is, I can only provide cooling to my equipment or I can only provide heating to the equipment. When you go to the 4-pipe, I'm providing hot water and chilled water 24/7 typically. And so that indoor unit can either go into heating mode or cooling mode simultaneously of the unit that's adjacent to it. But you bring up a great point. As we're heating and cooling simultaneously on these systems, we get some really nice efficiency benefits. AHRI, they had to basically come up with a new efficiency term or standard, SCHE, which is simultaneous cooling and heating efficiency, which applies to all manufacturers that have some sort of heat recovery equipment. Because of the efficiency, you have your interior spaces that we need cooling during that interior space, regardless of the outside temperature. So we're sending liquid refrigerant to the indoor units. It's evaporating off, pulling the heat out of the space, and we're going back to that branch box. Instead of just going out to an outdoor unit and rejecting that heat, there's some heat, hence the term heat recovery. There's some of that going on in a system like that.
Right at this point, we're talking about sort of system selection. What are some of the other system selection considerations?
Well, we could talk about there's water cooled and air cooled. depending on what kind of, maybe you have a boiler cooling tower plant already incorporated in your building, but you're trying to revamp everything. Maybe you have a geothermal system. Those are pretty popular for a long time. They still are, especially in our area. So you can go in with a water cooled and get all the advantages that you would get with a VRF system, and inverter compressors, that heat recovery, the small zoning that you're able to do by putting a cassette in every room or a ducted unit in every room. You get all those features, but you still get the energy benefits of being tied to like a geothermal loop or a cooling tower. You could go with an air cooled, and typically nationally, I would guess that most of the systems going out are going to be air cooled. It's going to be a lower total install cost. You don't need a geofield. You don't need a cooling tower. You don't need a boiler. You don't need extra pumps. So obviously a lot lower install cost, but you can still get high efficiencies up in the upper 20s of the IEER, which brings me to another point. One of like my pet peeves is people talking about SEER ratings all the time. SEER rating, SEER rating. From what I understand, a SEER rating is how efficient it is at 100% cooling capacity, correct? For the most part.
Yeah. So, I mean, SEER rate, this is a funny topic because EER is so simple. EER is always at a given point. At any point in time, you can tell exactly what the EER of a piece of equipment is. We're just dealing with capacity and wattage. That's it. But SEER, you've got to read a whole book in order to figure out the design conditions, because what they're essentially saying is the true SEER, seasonal energy efficiency, would be the average over an entire cooling season. So you would look at all the shoulder seasons, you would take all those measurements. And in fact, you could take some monitoring equipment, measure the wattage of the entire piece of equipment, measure the capacity, and average it over. And you could come up with what the true seasonal energy efficiency is of that piece of equipment. But the challenge is that you have to standardize it. Obviously, it's going to be different in Florida than it is somewhere else. You have maybe higher ambient temperatures and all this. And so a lot of people have felt like the rules are a little bit tilted and maybe aren't the best representation of reality, especially across the country. And so I think, again, IEER, I don't know what the standard is there. Maybe you can inform me on that. But my understanding is that there's been a big move to try to make it a little more realistic, especially regionally.
Yeah, so I think it's a lot more, much like the SEER rating, they're looking at how many hours you're going to run at 25%, how many hours you're going to run at 50%, 75%, and 100%, right? Because in reality, when we have multi-stage equipment, or in this case, inverter equipment, we're very rarely running at that 100% heating or cooling capacity. So that SEER rating is more tied to that 100% capacity, where the IEER is looking at, when I've looked at some charts and stuff, I don't have anything in front of me, but really most of our time is spent in that 25% and 50% capacity range. So now we're looking at where we're actually running at and the efficiencies you're getting. I mean, if I only need 4 tons of cooling, but I'm still hooked up, I'm still part of that 12-ton condenser, I become a much more efficient system. So I may have an average SEER, nothing impressive, but then when you look at the IEER, which in my opinion is going to be a lot better representation on how efficient that equipment is, it becomes really telling. I've had cases where I got a rooftop with inverter compressor, and I'm kind of jumping off VRV here for a minute. And I'm thinking specifically our Rebel unit. It's actually a rooftop unit with a Daikin VRV compressor in it. But the SEER rating's not that impressive, right? The efficiency at 100% capacity isn't anything that's super competitive compared to other equipment. But then when you look at the SEER or the IER rating, it just blows a lot of the other equipment that's doing like digital scrolls and things like that. I kind of went down a rabbit hole there talking about SEER ratings, IERs. It's one of those things. People will question me, well, how come that SEER rating isn't all that good? And I kind of chuckle and like, well, it's kind of an irrelevant value because our bin hours at 100% capacity are just so low.
And that is where IER is integrated instead of seasonal. And so it is looking at part load conditions and is much more reasonable when you're dealing with truly variable equipment. And of course, VRF, VRV being probably the most extreme example of extreme variability. I just said extreme twice. I'm being extremely extreme.
That's double extreme.
Yeah, totally extreme, man. It is the most variable of the variable out there. So looking at it from SEER definitely isn't the whole story. So water-cooled is an option. Air-cooled, obviously, most common. What are some options for low ambient conditions? Because obviously, I'm in Florida. VRF, VRV would be great here, other than maybe some of the condensate management issues, which I'll ask you about in a little bit here. But what about areas where it gets really, really cold and you're still expecting to heat with this technology?
Yeah. So like our climate, this is the biggest deal. For years, that has been the Achilles of VRV. How are you going to address those minus, I think our design conditions, most of our engineers, it's anywhere between -9 and -15 degrees Fahrenheit that we're designing our equipment to. So there's two problems there. Either I'm derating so quickly that I'm not getting enough heat, right? Like that's the fear. Or my engineering data stops maybe at -13. For a long time, Daikin only had engineering data down to -13. So beyond that, the equipment would run, but we were having a hard time showing engineers, well, they want to know exactly how many BTUs they're going to get out of the equipment at these design conditions. So that's always been kind of the Achilles heel. For a long time, water-cooled was a big solution to that, right? Because water-cooled doesn't care what the outside ambient is, cares what the water temperature coming into it is. So that was an option. Again, like I mentioned earlier, that's typically a little bit higher install cost compared to the air-cooled. So a popular option would be to use your standard air-cooled equipment, put it in a penthouse, and now we're going to duct that discharge out. Like, so in normal operation, everything's ducted out. I'm pulling air through my outdoor air intake louvers. As I'm, let's say, air conditioning, I'm discharging that hot discharge air through my ductwork and out of the penthouse. In the event that we start to get cold outside, eventually, let's pick a set point. And really, the set point depends on utility rates and what they're trying to do. So there's no hard, we want to switch over at 30 degrees or 20 degrees or 40 degrees. I kind of see it all over. I've seen it as low as 0 degrees. But once we get to whatever that set point is, we're going to close our intake air dampers, right? We're going to close the discharge air dampers, and then we're going to open a bypass or a dump damper, typically located on the side of that plenum or that discharge ductwork. So all we're doing now is just recirculating the air. As we dump it out, we recirculate. We always talk about we don't want to do that typically in air conditioning, right? We want to avoid recirculation of that discharge air, but this is what we're going to want to do. So ideally, we're going to be in a shoulder season, and what you'll see is a lot of the systems that have a cooling dominant mode, they're going to actually still be dumping hot air into your penthouse and doing a lot of heat recovery from system to system. If it still continues to drop in temperature in the space, we're going to have auxiliary heaters, maybe a hanging gas-fired heater that can pick up the slack. As we become more and more heating dominant, that gas-fired heater is going to pick up and maintain 35 degrees, let's say. So as we'll go with 45 degrees. We're going to shut our outdoor air dampers off. It's going to hopefully heat and cool each other for some period of time. As it drops down to 35, we might bring on some gas-fired heat, some sort of auxiliary heat. That's kind of, in my opinion, that's still a Cadillac way to do it. We get all the equipment inside, out of the elements. Coming from that service tech background, I really like the idea of being able to walk into a penthouse and turn that set point up to 55 degrees and work in really nice conditions. I would say that is a really Cadillac way to do it, a low ambient situation. Another way to do it is keep using that standard air-cooled equipment, put it out on the roof just like you would anything else, but we're going to rely on maybe hydronic hot water coils downstream of some ducted units. Maybe we'll rely on some fin tube heat on the exterior. We can control those heaters, those auxiliary heat. Maybe it's electric heaters downstream. You name it. I can control it through the control system through the use of dry contacts. And I can set that auxiliary heat up to act as a second stage. And with the option, I can actually utilize that auxiliary heat and use that as the primary heat and lock out the heat pump based off outside air temperature. So that's what I have actually like at my house. I have a gas-fired furnace, but then I got a VRV condenser that's hooked up to an actual cased A coil. That's a VRV cased A coil. And then at 20 degrees, it's either 15 or 20 degrees. I can't remember what I have it set up at. So heat pump is primary heat. In the event that I do need second heat, it will bring on my gas furnace. And then at 15 degrees, I lock out the heat pump, and then I just bring on gas furnace as my primary source. I always meant to look at the utility rates and do the calculation to see exactly where I want to be, but I just did 15 to be safe. I meant to go back and do that. It might even be closer to 10.
That's what they call economic balance point, I think, if you're going to be fancy.
Yeah, there we go. Thanks for the assist on that one.
Yeah, I just had to drop the economic balance point. That's a big one in NATE. If you're ever going to be taking your NATE test, they really want you to know a lot about economic balance point. Just a little FYI. Is that cheating? I don't know. I don't know if I'm allowed to give away NATE answers on the podcast, but I'm not sure. I'll have to ask the great Nate. What is this Aurora thing? That's a fancy sounding thing. What is that all about?
I mean, it's just like our standard VRV equipment, but we're using a little bit different compressor technology. There's some other components in there, like there's a brazed plate heat exchanger, but it's doing some vapor injection stuff. There's other manufacturers that have some low ambient, high heating equipment out there as well. Basically, the gist of it is we have that third port on our compressor. So not only do we have our hot discharge gas port, and then we got our suction port, we actually have a vapor injection port that allows us to maintain our capacity at a better rate as we drop off in temperature. So for these low ambient climates like ours, I mean, it's just taken off like gangbusters around here. They've been actually using it in Canada for a few years now. But the big thing is they got engineering data down to minus 22, which was a big deal. Engineers can now go, okay, yeah, I want to design to minus 15. I know exactly how much heat I'm going to get out of this piece of equipment at minus 15 degrees. So that's become a big deal in the consulting world. Like I said, we got that 3-port compressor that's doing vapor injection to maintain capacity, along with the brazed plate heat exchanger that acts as an economizer. It's doing some other things too. It makes a lot more sense when I get the refrigeration diagram out and really like, okay, let's follow the refrigerant around, right? And then it's got some things like some lower temp rated electronic expansion valves and things like that, since we know that piece of equipment is going to sit outside.
Frankly, you lost me with this vapor injection and brazed plate heat exchanger, but maybe that's the sort of thing where people have to attend your class to understand your deep knowledge on this topic.
Yeah, I don't want to get too much into actually what's going on. It makes a lot more sense when I have like slides in front of everybody. And like I said, you can follow that refrigerant around. It makes a lot more sense. So it's pretty neat stuff. The other cool thing is got our standard VRV4, which is our standard heating unit, and the Aurora. They both utilize the very bottom circuit of that outdoor unit acts as hot gas all the time. And it's doing two things. So the main thing is I want to make sure that as I go into defrost and things like that, I don't want ice or that moisture to freeze back into ice. So I keep that bottom row hot all the time to make sure there's no ice being built up. The other thing it's doing, once it condenses into liquid, it's cooling the inverter board. That refrigerant's passing on the backside of that inverter board, keeping it at a more consistent temperature, regardless of what our outdoor ambient and condenser fan motors are doing. What's kind of cool about that is I kind of pitch it to the engineers because when we're looking at some of the other manufacturers, I don't want to get too much into Daikin's better for this, whatever. But it's kind of neat because that bottom base pan heater is included in the consumption and the electrical data, the efficiency data. A lot of the other manufacturers, if you open up the service manual, they'll show that, well, when you're in freezing conditions, they want you to add a auxiliary base pan heater that comes on and stays on once you drop below 39 degrees. So when you're looking at efficiencies and things like that, that piece of the pie is not included. Plus, there's no extra electrical feed or anything like that that's required to be ran out to your outdoor units. So that's kind of one of the neat features. Uninterrupted heating during defrost, right? So I don't want my outdoor units to go into defrost and now suddenly I've taken heat away from all my occupants. You think of a traditional heat pump, you might have some electric strip heaters or something like that are going to come on. Well, in this case, I might have wall mount units or 2x2 ceiling cassettes. I don't have auxiliary heat downstream of that. So it's important to have uninterrupted heat even when I go into defrost. How it does that, it just defrosts one chassis at a time. Again, like some of the other manufacturers when they see one outdoor unit call for defrost, they'll actually tell everything, hey, we need to go into defrost and defrost everything in unison instead of one by one. That's kind of the different types. There's 4 different low ambient solutions. You have the water cooled, which is pretty plain and simple. You can put your standard equipment in a penthouse, duct it out, use some auxiliary heat. You could stick your standard equipment on the roof and then rely on auxiliary heat inside the space directly. Or you could go to a low ambient, high heating unit, like Mitsubishi's equivalents, like the Hyperheat. So the Aurora and the Hyperheat are very, very similar in the way they're doing things with that vapor injection.
That's sort of the system selection side on your different options, the types of equipment that you're going to select. Now let's start to talk about sizing. And let's start with the outside unit, because I think that's when people think about design and selection, that's one of the first things they think about is sizing.
Yeah. And I can't stress this part enough. Like, it's so important. Every time I have a chance to talk to an engineer that's trying to lay this equipment out, I try to bring it up 4 times. I can't hit home enough. I think it's a bigger deal in our climate because we look at nominal capacities. Typically, those nominal capacities are rated at 95 degrees outdoor, probably 78 degrees indoor. somewhere around there. But regardless, you go to Florida, you might see 100 and I don't know what part of Florida, but you might see a little bit over 95. So that nominal is going to be off a little bit, right, in cooling. But in heating mode in our climate, that nominal capacity does not represent the actual output of the VRV condensing unit. There's so many other variables that get put into it. A lot of the major factors, I already mentioned outside air conditions. Here, we typically size, like I mentioned earlier, -9 to maybe -15 in some applications. So I want to know what those outside air conditions are. What's my worst case scenario? What's my indoor air design conditions? Am I trying to maintain 68 degrees in the space during winter? Or am I trying to maintain 74 degrees space in the winter? And also in the summer, I got to know my humidity conditions that I'm trying to maintain. So those are two that are we commonly get those. Everybody kind of knows we need to know my outdoor and indoor air conditions. Another big one, though, that gets missed almost 100% of the time is your piping total equivalent length. And what that means is what's my total distance? And I would say when you're trying to put it on a schedule or get pricing or select equipment, I need to have an estimated total distance from my outdoor unit to my furthest indoor unit. The catalog has it all estimated at 25 foot. And that's from manufacturer to manufacturer. They're all the same. It's either 15 or 25. I might be wrong on that. But it's a very short distance, much shorter than real life application. I mean, a lot of these systems, your farthest unit might be 500 feet away from your outdoor unit. So what happens is once you figure out what that is, there's a multiplier that gets applied to that nominal capacity, right? So you might be 92% of your nominal capacity. So each one of these conditions will give you a multiplier on, well, outdoor air, that's going to give you this multiplier. Indoor air, it's going to give you this multiplier. Piping total equivalent length, it's going to give you this multiplier. Those are three of the major factors, in my opinion, that go into how much actual capacity you get of your outdoor unit. So you also need to know what your block heating and cooling loads are. You mentioned earlier, there's a lot of diversity that plays into this. So instead of saying I have 10 individual zones that all need 12,000 BTUs, so I'm going to sum up the peak of all of those, I'll probably look at the building as a whole and say, well, how many BTUs will I need at one time? A lot of times you don't need to add up all your zones and then prepare for worst case scenario, right? So we refer to that as a block heating and a block cooling load. And why it's important, that piping total equivalent length, it's important because one manufacturer might derate at a faster rate. As you get longer piping lengths, manufacturer A may derate at this rate, where B, they're another 5 to 7% less than their nominal catalog capacity. So that's why it's a big deal to get that called out. And all those multipliers that I mentioned earlier, it's not that I'm using my calculator and taking nominal capacity and punching in all these multipliers. This is stuff that gets put into the software. And as far as I know, all the manufacturers in their selection software has a point for that total equivalent length, because just like me, they want to make sure that they're covered on their capacity as well. Some of the other minor factors, which the first one that I kind of scratched or put down there is defrost reduction. In my climate, when I'm talking about -10, there is such a small amount of moisture in the air at that point, defrost becomes a very, very little factor. Defrost is a bigger issue if I'm sizing for winter conditions of, let's say, 30 degrees, 25 degrees, because I got more grains of moisture in the air, which is going to cause me to actually frost up at a higher rate. And I'm going to need to go through more defrost cycles, causing me to take a bigger hit on my nominal capacity. So I call that one a minor factor. And it's minor because it is in our climate. I typically tell guys, don't worry about that. And again, that's all factored into the software when you're picking design conditions. A couple of the minor factors, I would say piping heat loss. If you have really long lengths and there's poor insulation, again, I would find it hard to believe that somebody's using that in a factor or on a schedule or something like that. And then there's also connection ratio. Connection ratio it's basically a ratio of your indoor equipment to your outdoor equipment. So if I have 10 tons of outdoor equipment and I have 13 tons of indoor equipment, I have 130% connection ratio. So that connection ratio plays into your multiplier as well. Like I said, like 3 times now, the selection software for each manufacturer, they're going to do all that calculating for you. But if you don't give them the outside air conditions, inside air conditions, piping total equivalent length, they have no way to factor that. If you don't give them the piping total equivalent length, I would venture to guess that a lot of them are leaving it as the default 25 foot. Does that make sense?
Yeah, that's huge. And when you talk about design conditions, this is a moment for us to pause and remind everyone that this is not just true of VRF, VRV. This is true of all equipment. If you're using AHRI conditions, which AHRI design conditions are 95 degree outdoor dry bulb, 80 degree indoor dry bulb, and I think it's 50% relative humidity, those are not realistic conditions for the majority of the United States. And so you have to make adjustments. And you can look at your ACA tables if you want, or you can just be realistic about how the space is going to be used, which in my opinion is a superior way, so long as you're not padding. Don't choose 98 degrees as your outdoor temperature just because maybe once in a blue moon it's 98 degrees. If you want to get really crazy, you can actually look at how many days there are at each temperature, what the likelihood are for pretty much every locality in the US fairly easily. So you don't want to pad, but you do definitely want to make sure that you are covered, because when Jordan keeps talking about nominal capacity, that means when you look at the model number of the unit and you can see what the tonnage is, that does not represent reality even on a design day, frankly. I mean, you can have talking again, not about VRF, VRV here, but about typical air conditioning. You could have a 5-ton Carrier unit that is producing 56,000 BTUs on a design day, let alone a non-design day. And so you really want to make sure that you're paying close attention to that. And obviously, when you get into this scale of design, I'm going to say it now the fourth time, the design software is what you rely on. You're not just pulling this stuff out of your rear end. That's not what you're doing.
Right. It's funny because today I was doing the install and commissioning class with like 20 students here, and there's quite a few slides that talk about piping limitations, do's and don'ts. You can only be from indoor unit to indoor unit. I can only have 100 feet of elevation difference, rule upon rule upon rule upon rule. And I tell everyone, okay, guys, you got to walk out of here and remember all these rules. And they kind of look at me with a blank stare, and I chuckle like, no, absolutely not. Like sometimes I don't remember what these rules are, but that selection software, it's going to double check my work and make sure it's going to kick out an error if I try to go outside those rules. So
is right. All right, I'm going to take a quick second to talk to you about Speed Clean. We talked a little bit in this podcast about water source systems, and whenever you're dealing with water, you get the possibility of having scale. And whenever you have to flush a heat exchanger, whether it's a tankless water heater or whether it's a water source system, geothermal system, you have the potential for scale and you need to get it out somehow. And Speed Clean makes a bucket descaler. It's a really nice system. They have chemicals for it as well. And there's a lot of guidelines on how to do it. You can actually find out more about that on their site. You go to speedclean.com/product/bucket descaler. And it shows you exactly how to do it. And just a nice little product to have if you are in the water side, if you're working on the water side and you're dealing with heat exchangers of any sort. It's a nice tool. Even if you don't have it on every truck, you're going to want to have a couple at the shop for when you run into that sort of stuff. So thank you to Speed Clean for their support. Here we go. Back to Jordan. Okay, so now thinking about the selection and sizing of the indoor units or air handling units.
Yeah, so I'll probably say first, we'll talk about, we have branch selection discussion and talk about as well, on a heat recovery system. Am I going to stick with a single port box, or am I going to go to a 12 port box? Some manufacturers, I think they even have 16 port boxes out there. Mitsubishi's got some pretty crazy big branch selector boxes. I forget what they call them. Branch something. We all call them something different, but we'll call them branch selector boxes for my purpose. So there's different strategies. If you got a bunch of zones that are very clustered together, you're probably going to lean towards that larger port box, because you can go to it and then go from line set to each one of your zones that are clustered in a tight area. If you have very large zones that are covering a big area, you might go with single port boxes, or maybe just 4 port boxes. It kind of depends on how much hard piping you want to do, how much straight copper you want to do, how much line sets you want to do. The more single port boxes you do, or more lower port boxes you use, there's going to be a lot more brazing involved. And then the biggest thing I can say about branch selector boxes, I'm a big advocate of using isolation valves. I try to push that. It's not a requirement I don't think any manufacturer requires it. I think I go back to that hydronic reference. I would never want to go into a building and put in a brand new hydronic system and not give the service guy down the road any way to isolate a section of that system. If I want to maybe build a system out, or build an area out, add another unit, maybe I need to drain a unit down. I'm talking hydronics here. I want to drain a system down, a wing down, to make some changes. I don't want to have to take the whole plant down, the whole building down, because that becomes a really, really big interruption to the end user. I can't stress enough. I encourage isolation valves as much as possible. Typically, I see that on the outlet of the branch selector box going to all the zones.
So I'm thinking, okay, isolation valves going to the indoor units. And then do most of these indoor units have ports on them of some sort, or do you want to have ports there as well? So that way you could maybe shut off and then recover or evacuate a segment independently.
That's a great point, Brian. We want to use fully ported, right? So we don't want to have any pressure drop. And then we want to have those access taps on the valves, point them downstream, ideally. So a lot of times I'll put in, if I only need 7 zones, I'll put in an 8-port box with the intent end user. Hey, you have this extra port. We're going to put some ball valves on there. When you're ready to build this extra space out, you go ahead, you install your indoor unit, you run your line set, you tie on, you have the taps there. So you're able to purge your nitrogen, you're able to evacuate. You tell me how much feet you have, line set, and I can tell you how much refrigerant you need to add to that section. And then we go ahead and simply shut down the system, open up our valves. We turn the system back on and tell it to go look for indoor units. So if we had 19 units on that system, it's going to say, hey, I found 20. And then you just basically recommission it with that 20th unit on there. So it makes for a lot more pleasant experience for the end user. Instead of having to take an entire system down for 2 days, their heating and cooling is only interrupted for 15 to 30 minutes at the most.
We're kind of glossing over this, but that seems like a significant, like if you're going to be designing this system, you're going to follow the system design software, and it's not necessarily going to tell you to include this. So engineers who are listening to this, take that into account. Go ahead and do that. In a lot of cases, I think of VRF and VRV similar to rack refrigeration. And so you are thinking in terms of like a central plant, and you've mentioned this a couple times in the hydronic metaphor, but it's almost like your condensers are sort of like your rack room. And so why wouldn't you have, or in this case, we're talking branch boxes, but in refrigeration, you would never have a segment of the rack going in and without having ball valves in place and taps. That would be complete heresy. So why wouldn't you follow that same concept on the VRF, VRV side?
Thanks for bringing that up.
Okay, so we've beaten this dead horse. So now what's next?
So then you mentioned indoor unit selection, right? We talked about what kind of outdoor unit we want, how we're going to lay out our branch selector boxes. And then we have a wide plethora of indoor units we can choose from. We have multiple ducted units, depending on what kind of static pressure I'm looking to hit. I can do a low, medium, or a high static slim duct. I can do a multi-position air handler. I think a lot of manufacturers have that available anymore. Looks like a North American air handler that you would see on a unitary system. We got large tonnage ducted units, so you can get a ducted unit all the way up to 8 ton. You have the concealed floor mount, which is probably going to be hid behind like a soffit or something like that. You see that every once in a while. And one that's becoming more and more popular, I'm seeing it being used a lot, is the air handler integration kit. I mean, you can essentially take any air handler out there. I don't care what name's on the side of it. If it has a 410A rated coil, and I'm oversimplifying a little bit, there are some range in the volume of capacity, like actual internal cubic inches of that coil I have to hit, but that's all part of the selection stuff. So I don't want to oversimplify how it is. I can't just take any coil. It's specific, but I can take an air handler, add a specific coil to it, and then make that air handler a VRV unit. And it's simple as I give it an electronic expansion valve. So instead of piping up your TXV on your air handler, I pipe up my electronic expansion valve to my air handler. And then I just add a control box to it. That control box acts just like one of the other indoor VRV units. I have a couple pipe thermistors. I got a return air thermistor. And then I hook up my navigation controller or my thermostat to it. So now I've taken that third-party air handler. Again, it doesn't care what brand it is. It just cares that there's a refrigeration DX coil in there. That's going to act and run in unison with the rest of my VRV equipment, like any other unit. Something that's becoming really popular in our area is unit vents. So a lot of schools have those unit vents that sit under the window and they're pulling in a lot of outside air. I don't know. Do you guys have those down in Florida?
I've never even heard the term unit vent before in my life.
Sure. Because as I'm saying it, a lot of times they're just hot water or steam only. So that's all like, I don't even know if you guys have those out there. So a lot of these old schools that are still, they have heat only. They're pulling in large amounts of outside air to meet their ventilation requirements. They're coming in with these unit vent replacements and they're tying it into a VRV system, right? So I can, instead of having a compressorized unit that's slamming a compressor on and off. It does a horrible job dehumidifying because of the amount of outside air I'm bringing in. We can tie all these unit vents into a centralized VRV system. It becomes a really, really nice end product for the school. They take care of the humidity issues. They get cooling, which is awesome for them because they're used to heat only. And it's super quiet. So that AHU kit's been becoming more and more popular. I can do up to 16 tons per circuit, right? So if I had 2 coils, I could do a 32-ton air handler all off of VRV condensers. So it works pretty slick. The other caveat is I can actually do discharge air control. So if I want to do an air handler and I can give it an outside 0 to 10 volt DC signal, and I can ramp that discharge air as low as high as I need to within a reasonable range. So that works well when we're doing like ventilation, things like that. That's kind of covers it for all the ducted units. I might back up real quick though. On the high static ducted unit, there's a damper kit that you can get. And I bring this up because it makes sense. I don't know if the audience is all familiar with ASHRAE standard 15, has to do with how much refrigerant can be going through the space based on the smallest occupied zone. And I'm simplifying it a bit. But what happens is we'll run into trouble if we try to put a cassette in each 10 by 10 office, a bunch of 10 by 10 offices, and you put it on a very large refrigerant system, you'll get into trouble with that ASHRAE standard 15. If you put it on a ducted unit and they each have their own damper, I now get to add all of those offices, add the space up, and now I no longer have those small offices to deal with. Does that make sense? I feel like I did a horrible job explaining that.
My eyes glazed over as soon as you said ASHRAE, because ASHRAE standards for most of us are like, oh my gosh. But yeah, it makes sense. So you have a very small room, and having a separate evaporator in that very small room could cause problems because potentially you could actually have enormous amounts of refrigerant in that room if there were a significant leak. That's the idea, generally speaking, right?
Yeah. So we put it on a ducted unit. So now if I duct it, I get a share. We're sharing air. So I get to add all those spaces up together. So I can put the damper kit on there. So each office, the downfall of the ducted unit is I've lost the zoning, right? It goes back to like the old VAV design where everybody's fighting over the thermostat. Then you put that damper kit on there. And now I can take a ducted unit with the damper kit. Everyone gets to have their own zone control. And because I have an electronic expansion valve, I don't care what my minimum and maximum airflows are. The expansion valve is just going to compensate accordingly, whatever your demand is.
Quick question that just popped into my mind, as questions often do. Did you see Carrier at AHR? Were you at AHR?
I didn't go this year. I saw you in Chicago. It was great. There was butterflies and fireworks, but no, I didn't make it down this year.
Well, and then I actually thought about it afterwards. I was like, wait a second, I didn't see Jordan. If he was here and didn't, I'm going to be super ticked off.
Oh, I would have looked you up.
All right, I appreciate that. But Carrier had their Toshiba VRF thing. They were showing like basically rooftop units, connecting rooftop units to VRF. Have you seen that at all? Or it's basically the same idea, I guess. You're essentially just using the coil.
It's funny, Ryan Finley and me were talking the other day about this because he's like, oh, did you see Carrier? They came out with a DVS unit. So yeah, Daikin's I mentioned earlier, they have the Rebel rooftop, which is a gas-fired unit, standalone inverter compressor. But they also have what they call their DVS unit. So I can tie multiple, it's going to be a roof-mounted air handler. And yeah, so it's going to be tied into a separate VRV condenser. And I can do, I think, up to 3 of those DVS units. And I got hot gas reheat, so I can get neutral air out of it. And it's doing the heat recovery through the system. So I'm actually 3-pipe into each air handler. And I haven't seen Toshiba's, so I don't know the exact similarities, but it sounds like they're doing a lot of the same things. What's nice about it is it's packaged, right? Like I don't have to do a custom air handler and me going through the coil data to make sure that it meets the specifications. That type of stuff, I can check a box and go, yeah, I know it's going to work. The sales guys like that when they don't have to do a lot of research to make sure that it's going to work.
Sales guys enjoying not reading. That is shocking. Of course, that's not just sales guys. That's basically everybody in the entire industry really is happy when they don't have to read.
I do absolutely tons more reading of IOMs than I ever have as a service guy. I'm serious. I didn't expect that I would be more in depth and in tune with what was going on with some of this equipment logic than I am, but it's increased tenfold.
Yeah, but you also do CrossFit, so that proves that you are a nerd already. So.
Why'd you have to go and tell the world that? Oh, man.
Basically, if you look up Jordan's social media, it's like one CrossFit bro pic after another.
You son of a gun.
Interspersed with Axe body spray commercials.
That's right. I blame my girlfriend. She made me do it.
Yeah, it's good. I went through a short stint of that as well because I am definitely a nerd. Well, I know I'm a nerd, but I just don't have the self-discipline you have to actually keep doing it. And I like how I feel fat. So there's a bunch of other things. So we get into controls and some other design considerations. So I'll just let you walk through whatever the heck else you want to talk about.
And I didn't really mention any of the non-ducted units. I think the big one is the cassette, the ceiling cassettes. And I personally like the non-ducted units a little bit more. You get efficiency bonuses from that. I mean, if you think about it, we're not removing or adding any BTUs to a space when you're spending energy to just distribute air throughout a space, right? You have the larger air handler mentality. You're spending a lot of money, a lot of energy just moving air around. If you can go to cassettes, you spend a lot less money and energy to move that same air around and put that money energy towards actually removing or adding BTUs. So I tend to always push towards the cassette style, sometimes for like ventilation requirements, things like that, or just pure tonnage. The space needs a lot of tonnage. I'll go to that ducted unit. But there's a lot of different styles of different cassettes. You got the 2x2 cassette for the larger up to 4 tons. You can go to 3x3 cassette. Everyone's familiar with the wall mount, right? It's everyone's least favorite indoor unit, I think. There's the exposed floor mount. There's a one-way flow. We even have a surface mount cassette, right? So if you don't have a drop-in ceiling, you got a hard lid, and you want that 4-way cassette design, you could actually do a surface mount, which is becoming a little bit more popular.
I know what I wanted to ask you. This is the same question I asked John Oakes, and he gave me a totally unsatisfying answer, which is my biggest beef with ductless VRF, VRV in general is condensate. To me, that is in our marketplace as well. And I would condensate and maintenance. I'll kind of lump those in together. And maybe it's just because I'm in Florida. But do you find that there are any challenges related to condensate, any challenges related to getting people to actually maintain all of these separate units inside the space?
Yeah. So it's definitely not the issue. It must be there. This is not a hot topic in our area. It does get extremely humid in the summers here. And so specifically, are you talking about like buildup inside the unit or like condensate because the ceiling space, maybe the wet bulb is so high or the dew point so high?
All of the above, but primarily that you just have a lot more drains to clean, a lot more drain pans to clean. And then also we run into this thing in Florida where, what do they call the really thin blower wheels that they use in ductless and on the high walls? Because they're made of like the plastic carbon fiber material or whatever. There's a linear something blower. There's some term that's used there. Those get completely, I think the technical word is schmutzed down here. And we have to clean them. Like literally, I have one, I'm looking at it like right now in my master bedroom here. I have to clean it every single year, like physically remove the thing and clean it. And it actually gets wet. Like the actual blower wheel will hit dew point. And it physically gets wet and it gets all this buildup. So maybe that's just a Florida thing. And maybe that's what I'm asking.
What kind of relative humidity does like your space, what are you at? What kind of wet bulb or relative humidity are you guys at? I'm just curious.
Yeah. I mean, in the actual spaces, we will get up in the 60% relative humidity range. Yeah. It's a struggle, especially if you have situations where maybe you weren't running the air and then all of a sudden you do run it, or if you had the doors open or something like that. So it happens a lot. Obviously, we have outdoor dew points that can be over 80 degrees in certain circumstances. So that all kind of adds to it. And I think also another factor is that we just have so much crap in the air, so much living stuff that maybe you don't see. So maybe that's more of a complaint than a question.
Do you have like 24 people living there or something like that? I mean, that can't help, right?
Yeah, there's a few people.
24? I don't know.
Yeah, there's a few people living in this house, okay? There's a lot of laundry being done.
Oh, yeah. Yeah, I bet. Gosh, how many washers and dryers do you have?
We only have one of each, but they run like 24 hours a day.
Wow, I would imagine.
Like realistically, pretty much 24 hours a day, yeah.
To go back to your question, we don't see those issues. I'm thinking that we typically in our commercial applications aren't seeing that kind of space humidity. So I'm thinking that's probably contributing to it. I kind of came into this thinking we could talk about DOAS systems a little bit if we had time. I think that's probably a big part of it. If you got a good DOAS system that's taking care of your latent load, you're not going to have those type of issues that you're describing, I would imagine. Again, I don't have a lot of experience in Florida design conditions, but I would think if we can get that latent load taken care of with our ventilation air, and the VRV is going to do a phenomenal job removing any humidity that's left over. You're just going to see it's going to be so much drier that you're not going to see that type of issue.
Okay, fair enough. End of my question. Your answer was equally as dissatisfying as John Oak's answer. So now I dislike you both equally. All right, so what's next? What's the next design consideration here?
So, and I guess this one's not so much design, maybe a little bit. I guess I kind of had a note here to talk about like indoor unit turn down. Like we typically think of an air conditioner turning on or off. You either have cooling or you don't. When you're designing around an indoor unit and making your selections, I wanted to bring it up because it's nice to know what's going on. I think John touched on this a little bit on his podcast. So the biggest one that I talk about with customers is the auto fan logic. The fact that the indoor fan is actually being manipulated by a PI loop that's looking at set point deviation and time, right? So it's like a single, if you're familiar with the single zone VAV logic that we see a lot in high efficiency rooftop units, is as we get close to set point, I want to slow that fan speed down. I want to extend my run times. That way I can keep that cold coil for a lot longer time and I don't overshoot. So the longer I can keep that coil cold without overshooting, the better I'm going to do dehumidifying the space and having good turn down. The second part of that is we have variable superheat targets. So typically, if I walk up to a nav controller, I can look at what my superheat is, and I would imagine that it's going to be somewhere between 9 to 18 degrees superheat if I'm running cooling. So each indoor unit, it's the logic in it is monitoring its saturated temperature. So they got a temp sensor that's just downstream of the expansion valve, and then they're monitoring the leaving pipe temperature. They're just doing a simple calculation. Whatever our leaving pipe temperature is minus our saturated temperature, we came up with what our superheat is. Now, what they do for turn down purposes is they look at the delta T of the set point compared to the return air temperature. So as we get closer to our set point, I'm going to make that superheat higher. I'm going to make less of my coil active and get closer to like 18 degrees superheat. As I get farther away from my set point, the delta T, I'm going to make my superheat much lower, closer to that 8 or 9 degree superheat range. So I get more of my coil active and get more capacity. The third thing, Daikin calls it VRT. I think some of the other manufacturers are utilizing something like this. VRT is short for variable refrigerant temperature. And I keep mentioning the hydronic comparison, but it's much like a chilled water reset or a hot water reset. We don't always need 42 degree chilled water. We don't always need 180 degree hot water. Most of the time you can get by with 140 degree hot water and it does just fine. So what the outdoor unit's actually doing is it's looking at the conditions of the outdoor air temp, and it's looking at all of my indoor units and how far off of set point I am, right? And it's looking at the PI, how long we've been off of set point and how far we've been off of set point. So the inverter compressor is backing off as our expansion valves are closing off, right? Much like a hydronic pump, as you have valve shut off, differential pressure says you can slow your pump down. So the inverter compressor is doing the same thing. In cooling mode, is trying to hit a target saturated suction temperature, which correlates to a specific pressure. But what happens with this VRT, if the conditions meet, and maybe I'm not that hot outside, I'm 75 degrees, and most of my indoor units are close to set point, I'm going to reset my saturated suction target from, let's say, 42. That's typically the default. We'll go from 42, and I'll go as high as up to 52 degrees saturated suction temperature. So not only is my inverter backing off, but I'm decreasing the lift on my compressor. So it's a huge energy efficiency benefit, but I'm extending that runtime of that unit. So you design your indoor unit at a 42 degree coil, it gives you this many BTUs, but at a 52 degree coil, it's going to give you a much lower amount of BTUs. So between those three things, that auto fan logic, the variable superheat control, and then the variable refrigerant temperature, you get a dramatic turn down on all your indoor units. Something to note that not all the indoor units have the auto fan logic. The VRT, sometimes I will manipulate that, lock that in. I might disable it. So if I am relying on my VRV equipment to take care of not only my sensible load, but also my latent load, right? If I don't have a dedicated outside air system, I might want to lock that in at 42 degrees to make sure that I have a cold enough coil all the time to remove the enough moisture.
Well, that's immediately where my mind was going. I was thinking, well, I'm not going to use that in Florida.
Not in Florida. I'd probably avoid.
I constantly bore my audience because I'm always whining about how things are hard in Florida. Like none of us care. Shut up, Florida boy.
I lived in Phoenix for 5 years and man, it was hot out there. But yeah, we didn't have to deal with the humidity you guys have to deal with. It's a 1-2 punch.
I know, right? We've got it rough. We've got it really rough. Like today, it was like 75 degrees.
Yeah, that's tough.
And I was sweating and it's so upsetting. Yeah, I'm running my air right now. Jeez, it's rough.
We got 7 inches of snow. I think this weekend is looking at a low of -10. Yeah, things are looking up here.
You've got it good.
Needless to say, I'm very, very satisfied with my position this time of year.
Yes, meaning where you're not with us saps out there. When I say us, I like how I'm lumping myself into that. With all the technicians actually working out in the snow, freezing their fingers and faces to the bones. Yeah.
Yeah, I honestly miss it sometimes, though. I daydream about it on a regular basis. There's something that I still, when the field piece wireless probes came out, I had to get me a set. I love Measure Quick. Even though I don't get to use it ever, I get really excited when I do, though. When I get involved and I want to come out to a job site, I'm like, oh, I got just the tools. You wait. And everyone's super impressed with Measure Quick.
Yeah, well, as they should be.
That reminds me, I'm just going to let Jim know I'm super excited for the PC version because I'd like to do it on my Surface. That would be a big deal. I know he's teased us about it. And maybe I'm behind the 8 ball here. If it's already come out, maybe he'll say, hey, dummy, it's already come out. But I'm super excited for it to come out for PC.
Yeah, and that's sort of the future. And I don't know how much of that I'm supposed to talk about. I think Jim calls everybody. This is another little Jim secret. He calls everybody and tells them like stuff like, hey, don't tell anybody about this. But then he tells everybody.
You're right.
And I don't know if he's doing it intentionally to make you feel special or because he really just forgets who all he told.
Sure. Maybe he wants you to leak it.
Maybe. And so I'm going to right now. But one of the things that he's definitely planning to do is where the Bluetooth software can then connect via the cloud and then you can access it remotely. So you essentially can remote view Measure Quick devices that are in the field. That's a big future part of that as well. The web interface. So that will be cool for guys like you and I to still get the Measure Quick experience without having to get our little soft white paws too grimy. Because that's important.
Yeah, I don't want to get them too dirty.
Absolutely. Because that would hurt your CrossFit grip for sure.
My grip is impeccable.
Impeccable. Yeah, we're going to stop there. There's more that we can talk about with the dedicated outdoor air and controls, but we're already pretty far into this, and that'll give us something to come back to at some point.
Yeah, that'd be awesome.
So thanks for coming on. And if anybody wants to connect with Jordan, then the best place to do it, by golly, is in the HVAC School Facebook group. He's not in it as much as he used to be now that he's special, but if you get lucky.
Brian, tell you what, man. When I used to sit there on the roof waiting for my vacuum pump to pull down, that was prime time for HVAC school to pop up. And I just don't have that downtime anymore. I mean,
I understand.
I underestimated how many after hours I'd be spending in front of my computer in my kitchen trying to catch up from the day.
Mm-hmm.
But yeah, I still get on there and lurk every once in a while. I'm just a little bit less active than I used to be.
Hey, no sweat. We forgive you. And yep, if you want to bug anybody about VRF, VRV, Jordan's the guy to do it. He's just nerdy enough that he would love to answer some of your questions if he gets time. So yeah, thanks for coming on, buddy. And we'll do it again soon sometime.
Yeah, thanks, Brian.
The way people end the podcast always makes me laugh because you went like super sincere there at the end. Go ahead and try that again.
Well, I can't do it again sincere. You get one shot at it.
All right, man. Appreciate you.
I'm like a 12-year-old.
All right. Again, big thanks to Jordan. It's great to see people who have been participants in the HVAC school community coming on the podcast, writing articles, making videos. We've had more of that lately. More people who have something to say and they're saying it on HVAC school, and that's cool. It's good for the industry. You don't just need my stupid old voice. It's good to hear from other people. So, hey, if you ever want to send me something to put up as a tech tip or a video or something, just shoot me an email, Brian, Bryany for yeah. Brian at hvacrschool.com. That's the website, hvacrschool.com. If you haven't been to the website in a while, hey, I can't say that a whole lot has changed. There are a lot of new tech tips, of course, and new things there content-wise, but I haven't done much in the way of making the website look pretty, although that is in the works. We're planning to do that, but that's hvacrschool.com. Now, the application, the app, I think it's pretty good. I think you're going to like the app. So if you go to any app store, whether you're Android or iPhone, and you type in HVAC School, you'll find our app right there. Download it. Tell me what you think. I would appreciate that. I can't remember if I've repeated this one or not on here, but this is one of my all-time favorites. And so, what is the difference between a hub for buses that is quite gross, and there's a lot of details here, so you got to remember it's a hub for buses that's quite gross. What's the difference between a hub for buses that's quite gross and a lobster with a boob job? One is a crusty bus station, and the other is a busty crustacean. Oh, man. The first time I heard that, I think I laughed for about 2 hours straight. I'm sorry. Yes, I'm 12. Jordan and I have that in common. All right. Thanks for listening. We'll talk to you next time on the HVAC School Podcast.
Thanks for listening to the HVAC School Podcast. You can find more great HVACR education material and subscribe to our short daily tech tips by going to hvacrschool.com. If you enjoy the podcast, would you mind hopping on iTunes or the podcast app and leave us a review? We would really appreciate it. See you next week on the HVAC School Podcast.